Hey Chem 2, it's Dr. Ricardo. This is the third video, probably of four, in the series for chapter 19, which is on thermodynamics. So where we left off in the last one was we started to talk about standard entropy. So we know entropy is the degree of disorder that a substance has. And standard conditions don't reflect the temperature, but reflect that any partial pressures of gases are at 1 atmosphere and any solutions are at 1 molar solution. So you can look up S zeros for different substances in the back of your book. In your book, it is Appendix C on page 1088. And you see the three numbers that they tend to tabulate here. Let me see if I can blow this up a little bit more. Okay, are delta H0 of formation in kilojoules per mole. Something that we're going to learn in a little bit, delta G0 of formation in kilojoules per mole. And S is a much smaller number, right? So S is just S0. It's not a formation. It's the actual amount of entropy that those molecules have. And it's in joules per mole Kelvin. So the important thing is whenever you're working with S and delta G and S and delta H, that you convert these after you do your calculations. You have to multiply by the Kelvin temperature and then convert to kilojoules, because these two are in kilojoules and this one is in joules. So that's very important that you realize, otherwise you're going to get all the questions wrong. So you see, most of the numbers are positive. In fact, the only ones that you're going to find on here that where S is ever going to be negative is if you have ions in solution. When something becomes solvated, it actually loses entropy, has less entropy than the substance has in its free state. But all the other ones are all pretty much positive numbers. Okay, so we'll get back to that in a bit. Okay, so we talked about that. I'll just make this a little smaller. Good. And then the next thing we realize is that if I want to calculate delta S0 for any reaction, all I have to do is take the sum of the S0s from the table for the products minus the sum of the S0 for all of the reactants. So it's always products minus reactants, where we take into account the coefficient. So if there's a coefficient in the balanced chemical equation of 2, we would multiply S0 from the table by 2. If there's a coefficient in the balanced equation for nitrogen gas of 7, we would multiply by 7 here. All right, now, one of the things that sometimes we ask in multiple choice questions is, can you predict the sign of delta S for a particular chemical reaction? So here are some of the scenarios that you will see where you're supposed to have an understanding of what you're actually talking about when you're talking about the change of entropy. So delta S is the final entropy of the system minus the initial entropy of the system. So what are we looking for a positive delta S? Well, nature is always moving towards a positive delta S, so we want the degree of disorder to be greater in the products than in the reactants. So anytime you move to substances that are more disorganized, more separated, less homogeneous, but right, more heterogeneous, where things are all kind of mixed up in crazy random orders, those kinds of things are going to have a delta S that's going to be a positive number. So, first one, a reaction in which a molecule is broken into 2 or more smaller reactions. So any kind of dissociation reaction where one thing breaks up into many things, that's going to have a delta S that's positive. That kind of makes sense. That's more disorganization for the products compared to the reactants. Second, a reaction in which there's a net increase in the moles of gas. So you have more moles of gas at the end than you have at the beginning. So if you think of something like this, H2CO3 aqueous, right? So you have carbonic acid in water, okay? It's in equilibrium with carbon dioxide gas and water liquid. So when carbonic acid dissociates, it makes carbon dioxide gas and water. So you can basically add those back up. You see there's 3 oxygens and 2 hydrogens and 1 carbon. So everything balances out. Well, look, there's 1 mole of gas here, and there's no moles of gas here. So from left to right, I go from 0 moles of gas to 1 mole of gas. So delta N, the change in the number of moles of gas, is +1 because the products have 1 more than the reactants. Well, gaseous molecules have a huge amount of entropy compared to things in solution or liquids. So my prediction for this chemical reaction is that delta S would be positive. I'm going to more disorganization. First of all, I'm decomposing it. Second, more importantly, I'm going to more moles of gas, 1 versus 0. Okay, and the third one, a process in which a solid changes to a liquid or gas, or a liquid changes to a gas. So in any chemical reaction, even something as simple that's a physical reaction of something melting, that's going to more disorganization. Anytime you go from a liquid to a gas, a solid to a gas, or even a solid to a liquid, you're giving the molecules more freedom. They can be in more different states. Therefore, they're going to have a higher entropy. Okay, so those are 3 things that you should look out for if you're asked to predict which of these chemical reactions has the greatest delta S. Okay, all right, so new term. The last of our thermodynamic quantities, okay, so I'm going to put them all down in a second, is going to be, we're going to define it as G. And what G is going to be is we're going to call it the free energy of the substance. So the free energy G is a thermodynamic quantity defined by H minus Ts. Now all of these things are state functions, right? So anytime something is a state function, it doesn't matter the pathway on which you go from position A to position B. So just like you would expect for any of our other state functions, delta G is G final minus G initial. Again, independent of how you get there. If you know where you start and you know where you wind up, you can always calculate delta G. You don't need any more information than that, okay? Well, if G is H minus Ts, and delta G is H final minus H initial, you can go into here and make a G initial by putting all I's on everything, okay? And a G final by putting all I's on everything, okay? So this guy would have an I, this guy would have an I, this guy would have an I. Then you make a final. Make 2 different equations. Then you subtract the initial one minus the final one, and you can get delta G. So I'm not going to do that simple derivation, but you could do it if you want. Now again, as long as the temperature is constant, okay? So you keep the same T in the initial one, the one with the I's over here, as you do, and then what will happen is you can factor out the T. So if this is the case, then this is the case. Now, this one up here, guys, isn't very useful, okay, in the sense that you're not usually interested in the absolute free energy of a substance. What you are interested in is how much it changes in a chemical reaction. So this is a critical equation, maybe the most important equation of chapter 19. It's called the Gibbs free energy. So delta G, now this doesn't have any zeros on it yet, so this is delta G under any conditions of temperature, pressure, and concentration. Okay, whatever, you just tell us what those conditions are. What's the pressure? What's the temperature? What is the partial pressures of all the individual gases? And what is the concentration of all the solutions? If you tell us that, and you keep those things constant, delta G is equal to delta H minus T delta S. And obviously, like everything in this chapter, T has got to be in Kelvin, so you have to switch over to Kelvin. Okay, so that means if you know the delta H in that reaction and you know the delta S in that reaction, and you want to know, and they don't change very much with temperature, you want to know what's the free energy, you can use this equation to calculate the free energy. Okay, all right, so for this equation gives a direct criteria for the spontaneity of a reaction. Okay, if delta G comes out to be negative, not only do you know that it may be exothermic because it's negative over here, but more importantly, the reaction will occur without any external, without you providing any external energy. So you just put the reactants together under those conditions of temperature, pressure, and concentration, and they will react spontaneously. So spontaneously means no push. You just put them together and they'll start reacting. That's what delta G equal to a negative means. Okay, on the flip side, if delta G is positive, the reaction is non-spontaneous. You need to provide external energy. How much? Well, enough to make it go negative. So let's say this thing, delta G, comes out to 1.7 kilojoules per mole. That means you need to provide 1.7 kilojoules per mole from the outside in order to get this thing going. So if delta G is positive, the reaction as written from left to right is non-spontaneous. That means the backwards reaction would be spontaneous. For this one, the forward reaction is spontaneous. Going backwards would be non-spontaneous. Well, what's the middle between positive and negative? 0. Whenever delta G for any chemical reaction under any conditions comes out to 0, it means that you're currently at equilibrium. The forward reaction is occurring at the same rate as the back reaction, okay? That's delta G equal to 0. So this is a huge criteria, okay? All of these equations came out as a result of the as part of the revolution in the Industrial Revolution in the 1860s through early 1900s, when people were figuring out what was going on with steam engines all the way through combustion engines. So it's kind of the heyday of thermodynamics, was what I would say maybe 1860 to 1910. And that's the time when this idea of free energy came out. So from a practical standpoint, delta G in a spontaneous reaction, that number gives you a very important piece of information. Not only does it tell you that maybe it's exothermic, but it also has taken into consideration the entropy factors of that particular chemical reaction at the temperature that you're interested in. So delta G gives you the amount of free energy that can be used to produce work, right? If you don't calculate delta G and you just have delta H or delta S, you may be able to calculate some energies, but you won't be able to harness all of that energy. Delta G predicts how much energy can be used to drive a car down the road or do something practical. The work that you could possibly extract from that chemical reaction is delta G. And we'll talk about that a little bit later on. So it's very important. That's why they call it the free energy, the energy that's available to do work, the energy that's freed up to do work. Okay, so this page is a derivation of the Gibbs equation. It's page 9. It's very interesting, but because of a lack of time, I'm going to skip over it in terms of this video, okay? So what you wind up at the end is our 3 critical situations. If you're at constant pressure, okay, which we know we have to be at because we're working with delta H is equal to Q at constant pressure. So if you're at constant pressure, then delta H minus T delta S is equal to 0, yes, because delta G is equal to 0. Delta G, if 0 is greater than delta H minus T delta S, then delta G, right, is going to be a spontaneous reaction because delta G is greater than those numbers, okay? So in this case, delta G flipped over would be negative. These things are going to be less than 0, they're going to be negative. If this product of these terms comes out to be positive, you're still at constant pressure, but now you're a non-spontaneous reaction, a reaction that won't occur just by putting the materials together. You would have to provide some external energy. So that's page 9. Okay, so let's talk about delta G under standard conditions. So that's called the standard free energy of a reaction. So delta G 0 for the reaction under standard conditions. And what are standard conditions? 1 atmosphere of pressure for the partial pressures of all gases and 1 molar for all solutions. And whatever the stated temperature is, usually these things are tabulated at 298 Kelvin, which is 25 degrees C. So again, delta G in these tables is going to be 0 at 298 Kelvin. That's because this is not held in the little 0, but the tables have to be done at some temperature, so they're usually done at 298. Okay? All right, so let me show you where those, actually, I'll hold off till I get down to the bottom of here and go back to those tables. Okay? So under any conditions, we have the case that delta G is equal to delta H minus T delta S. We already talked about that. Under standard conditions, we just add little zeros here. Okay? That means that delta G, 0 under standard conditions, is equal to delta H, 0 under standard conditions, which is equal to T times delta S. Okay, so it's at a certain temperature. Obviously, the S, the H, and the G must all be at the same temperature. Okay, so we're going to use these two a lot. And then later on, we're going to relate the non-standard conditions to the standard conditions. Okay, tabulated in the back of the book, you're going to have 3 numbers that I just showed you a little while ago, and I'm going to show you again. But one of them is delta G0 with an F after it. Now, you'll remember this from Chem 1. F means formation. So let's review it. The free energy change, delta G0 of formation, is the free energy change that occurs when 1 mole of a substance is formed from its individual elements in their stable state at 1 atmosphere. And a specified temperature, usually 25 degrees or 298. And that's what you have in your book. Okay, so we'll talk about that in a second. So whenever I look up delta G for any element in its standard state, so for instance, if I look up delta G 0 for oxygen gas, O2 gas, well, O2 gas is usually found in the gaseous phase with both oxygens attached, so oxygen would be O2 in the gaseous phase. So how much energy does it take to make oxygen gas from oxygen gas? It takes no energy. It's already there. How much energy would it take to make carbon dioxide from oxygen and carbon? Well, that's going to have a number to it because it's not an element. Okay? How much energy, what is delta G0 formation for carbon in the graphite form? 0. Because that's the way you would ordinarily find carbon. That's its most natural state. Okay, and we'll look those up in a second. Okay, how do you work with delta G for reactions? Okay, so delta G for any reaction is equal to the sum of delta G0 of formation for the products minus the sum of delta G0 formation for all of the reactants. And again, take into consideration the coefficients. If in your balanced chemical reaction you have a coefficient of 2, you go to the table, look up the number, multiply it by 2. Guys, this really isn't for formation. This really is for reaction, for a particular reaction. So delta G0 for a particular reaction this is how you use it. Okay? All right. So again, delta G0 of formation, you can get from the tables. You could do the calculation yourself. They kind of did it for you, though. Would be delta G0 of formation of all of the reactants in the standard state minus T delta H0 delta S0. Because remember, this one doesn't come from formation. This one, they actually have the tabulated S's. Okay? So in the table, you really don't need this one. You could take this one and this one, which is given to you, this one and the S's, put them together and get the delta G. And what temperature would that be at? That would be at 298. Okay, so let me show you again. There's tons of these, so we're just going to look up a couple. Right? How much energy does it take to make aluminum from aluminum? Delta, what is its enthalpy? 0. What is its delta G? 0, because that's the way you ordinarily would find them. So each element in their standard state is going to be 0. So I'm interested. I'm going to look up carbon. Okay, carbon gas. That's not normal. You got to put a lot of energy. So that guy's got a positive number for delta G, delta H. Delta G has a positive number, and S has a number too. Okay, so here's carbon in the graphite state. Here's your 2 zeros. This is the natural form of carbon. Diamond is a little bit higher in energy than graphite. Okay, so elements in their standard state, that's where all these zeros come from. Here's cesium. 2 zeros and a number, right? Don't expect the S's to be negative. They won't be. Okay, let's go. Don't expect them to be 0. Okay, these two, you wouldn't have to look up. You'd realize that they're 0. Oh, last thing. Any one of these numbers from here, right? Delta G is equal to delta H minus T delta S. So if I have a particular chemical reaction and I get my delta S for that reaction, I get my delta H for that reaction, I should get the same exact, let's take this one down here. I should get this number by taking this number minus T times delta S. And what's T going to be? 298. So 298 times this, change it to Kelvin, and then subtract it from this should give you that. Okay, that makes sense that this is less negative than this because this guy came out positive. Okay. Okay, let's talk about what does the value of delta G tell you? If it's a really big positive number, really big negative number, or around 0. So delta G, 0, under any conditions, the table can give you that, right? So I can look up any one of these things over here. All right, delta G 0 for this stuff over here, aluminum chloride, minus 705. Wow, right? That's a big negative number. So big negative number means that if I tried to do the equilibrium constant for this reaction to make aluminum chloride solid from aluminum and chlorine gas, the equilibrium constant would be an absolutely enormous number. That means making this is stoichiometric. I could make it from aluminum and chlorine, and it would go all the way to the right. The equilibrium would be way over to the right. If you have something with a positive number, okay, you don't have that many with a positive number. Here's one. Right? If you have something with a positive number, that means, oops, sorry, let's go to here. Okay, we were doing aluminum chloride, so that's a huge oops, sorry, this one, negative 63. Here's one with a positive number. That means that the equilibrium constant to make this from carbon and hydrogen would be very, very small, okay? So we'll take a look at the notes, but delta G for any chemical reaction comes out to be a large positive number. Let's do large negative first. Large negative number, more negative than 10 kilojoules per mole. The reaction is spontaneous as written. The reactants transform almost entirely to products. The reaction goes completely to the right. So you can forget the back arrow. So those chemical reactions, we call them stoichiometric. They go all the way to the right. Okay, what happens if delta G0 is a large positive number, greater than 10 kilojoules per mole? Okay, that means that the reaction is non-spontaneous as written. The reactants do not give significant amount of products. If I put those two things together in a room, they'll only react a little bit to the right. If I put the products in a room, they would take off and make the reactants. If delta G is equal to 0, the reaction is at equilibrium under those conditions. Okay? If delta G0 is a small negative or positive number, the reaction is close to equilibrium. Okay? Positive would mean that it would be something like 0.1, or it would be its equilibrium constant, or 0.2, a small number but close to equilibrium. And negative would mean that its equilibrium constant would be greater than 1. All right, this is kind of neat. This is what I was talking about earlier, right? Delta G predicts the maximum amount of work that could possibly be extracted from the chemical reaction to do mechanical work or do something practical. Okay? Remember, the Industrial Revolution harnessed our ability to get into fossil fuels, use the heat energy that is contained inside the fossil fuels, and transform it into mechanical work. That's how internal combustion or steam engines work. They take the exothermicity of the burning of the fuel, of the combustion reaction, and harness it to make work. Well, how much work can you do? That's the free energy, okay? W max, the maximum amount of free energy, is equal to delta G. Okay, so let's read this up here. The free energy change of a chemical or physical process is the maximum energy available, or free, that's why we call it free energy, to do useful work. W max is equal to delta G. So maximum amount of energy is equal to delta H minus T delta S, enthalpy change minus the entropy loss. And usually it is a loss. Okay, here's an interesting case. You want to do this particular chemical reaction. You want to go into this business. You say, hey, I want to make iron out of iron oxide. Okay? Now, I don't want to have to heat this iron to ridiculous amounts of energy and put all of this free energy in, right? If I do go to the tables and I calculate delta G0 for this chemical reaction by looking up this guy. Now we know that guy is going to be 0. The formation, delta G0 formation for iron multiplied by 4. So 0 times 4 doesn't change anything. Plus 3 times delta G0 for the formation of oxygen. Again, since it's a formation, this guy's going to be 0. So I'm going to have 0, 4 times 0 plus 4 times 0. So I'm going to have nothing over there. Then I'm supposed to take the products and subtract off the reactants. So I would look up 2 times Fe2O3. If I do that, okay, and I subtract that off, I'm going to wind up with 1487. So I'm going to go look this number up for you in a second. Let's take half of that number, because that's what I think I'm going to find in the table, and one can also predict a sign. So if we have products minus reactants, this guy's a reactant, it's going to be minus this number, and then I have to take into account that this is for 2 moles. So I'm going to divide this in half and make it negative, and that I think is what we're going to find in the table. So you would have used the table going backwards to calculate this negative 1487. So 1487 divided by 2 equals 743 and a half. Okay, I have no idea. I'm guessing now. Okay, thinking on the top of my feet. All right, let's look up iron oxide, Fe2O3, which is basically rust. Okay, let's look up iron oxide's delta G of formation. Okay, and I'm guessing it's going to be negative 743-ish. Okay, negative 743. Okay, let's see what we get. So I'm going to look up iron. That goes by the base element. Fe2O3, I got a delta G of, I'm going to show you guys. That's the second one. This guy, where's my finger? That guy right here, right? Iron oxide. Delta G is the second column. See? Second column. I got minus 740. Well, really close, right? I was just telling you it should be minus 743. So that's where that number comes from. All right. So taking this number, using it here, if I take the number off the table and put it into here, I would, how would I get that? I would take the products, 4 times 0, plus 4 times 0 minus 2 times this. And that's how I would get that. So my negative 743 times 2 would give me positive 1487. Okay. All right. So I want to do this reaction, but I don't want to provide all of this energy. This is non-spontaneous. I would have to provide 1487 kilojoules for each 2 moles of this that reacts. So this number is for the reaction as written. If I wanted it per mole of iron oxide, this would be 1/2. But to do the reaction exactly the way you see it, that's how much energy it would take. Hey, I don't want to just waste energy. So what I'm going to do is I'm not going to try to do this reaction alone. I'm going to couple it with another chemical reaction that's exothermic, not only exothermic, but also has a very, very negative delta G that's incredibly spontaneous. And that reaction is carbon monoxide plus oxygen goes to carbon dioxide. Okay? So leave the first one alone. Multiply that second reaction of carbon monoxide plus oxygen goes to carbon dioxide. Okay? And multiply that through by 6. And what that'll do is that will take these 3 oxygens out of here and use them all up in the second reaction. So the draw is this one is going to provide the oxygen, and then the oxygen is going to be used up here. So the oxygen that's released from the decomposition of iron oxide to make iron and oxygen is going to be used up in converting carbon monoxide to carbon dioxide, which is very spontaneous. Okay? All right, put everything in, cancel these 2 out, and nothing else cancels out but the oxygens. So I wind up with 2 iron oxides, 6 carbon monoxides, go to 4 irons, and 6 carbon dioxide, right? These 2 guys are gone. Okay, what do you do to chemical reactions when you add up their reaction? You add up their thermodynamic quantities. So just like you would do with delta H, you do the same thing, right? If these were individual delta H's like Hess's law in Chem 1, you could do the same thing with delta S types of reactions or delta G types of reactions, which we have here. So put this guy and this guy together, sum them up, you're going to get a slightly exothermic reaction. So you can take something that's very hard to do, put it together with something that really wants to occur, and you get this net benefit. Okay, you also getting rid of all this carbon monoxide from the world, which is good. Now, where does that carbon monoxide come from? One source that you can get carbon monoxide from is from a coal gas. So you take the carbon monoxide that comes off of extracting the carbon monoxide from coal. And it's really interesting that you think about Western Pennsylvania. Pittsburgh is not only the capital, the steel capital of the world, it's also a coal, Pennsylvania and West Virginia are coal producing countries. So you have both of the 2 elements that you need to go into the steel industry. And that's what Andrew Carnegie did in Pittsburgh in the early 1900s, right? Late 1890s to early 1900s. Steel became the building material of our country, and Carnegie became incredibly wealthy. He's not only was the king of New York, or one of the kings of New York, he was certainly the king of Western Pennsylvania. He probably felt guilty for the way he treated some of the people who worked for him. So he made, beautiful museums and Carnegie Hall and all those wonderful things. He made Carnegie University in Pittsburgh, which later on joined up with Mellon University, and that's what's currently Carnegie Mellon University. But he was a great industrialist because they took advantage, right? They took advantage of these 2 processes. And what are you doing? You're making steel and you're getting energy out too, okay? So it's sort of self-sustaining, okay? So this is the reaction that occurs in a blast furnace when iron ore, mainly in the form of iron oxide, just rust, okay, is reduced to iron. And just out of curiosity, let's calculate what the oxidation state on iron is in here, like we would have in Chem 1, and then figure we know what we're going to. We're going to iron in the solid state that's got an oxidation state of 0. This guy's got all of its electrons, right? So what are you doing to these irons over here to get them from here into here? Well, if we go backwards, we know oxides are always -2, so that gives us -6. So that puts these irons in the iron +3 state. So I'm taking 2 irons in the +3 state, and I'm giving them electrons, right? Each one's going to require 3 electrons to get them to the iron in the 6th state. So this whole process is a 6-electron reduction. I need to put those 6 electrons in. So where do those 6 electrons come from? They come from the other parts of the chemical reaction. They come from the oxygen changing from oxygen -2 to oxygen 0 over here. Okay, so that's called, we're reducing the oxygen. Okay, last really important table. Okay, but anytime I put something sideways, it means it's important. Okay, I love this table. This table helps you to predict under what conditions a chemical reaction is spontaneous. Okay, so a lot of good understanding that comes from this table. Okay, all right, so let's take our time. Okay, we have two fundamental forces in nature that when you put them together and ask yourself, under what conditions will this chemical reaction become spontaneous or not? Here's what you want to say to yourself. Well, first of all, the first fundamental condition that we want is things are naturally want to go downhill. They want to be exothermic. Well, we know exothermic is delta H equal to a negative. Okay? The other fundamental concept that we want to have is, because we live in an expanding universe, things fundamentally want to move towards more entropy. So delta S is equal to positive. So whenever delta H is equal to negative and delta S is equal to a positive, when you plug into this formula over here, temperature is always positive. There's no such thing as a negative Kelvin temperature. So this part of it is positive, right? Because this guy is positive. And then if that's positive, this little part is positive, you put a negative sign on it. With the negative sign, you got a negative added on to another negative. Well, negative and a negative will always be negative. So, makes sense. This chemical reaction, these kinds of chemical reactions will be spontaneous at any temperature. Exothermic and more entropy. Yay! Yay over here, downhill. Yay to more disorganization. If I take a deck of cards that's beautifully organized and I throw them downhill, that's definitely spontaneous. They're going to make a mess and they're going down. So doesn't matter what the temperature is. Okay, let's look at the flipped over one, the last one here. Here's the situation where you would have to go uphill and get more organized. That's like taking a deck of cards, the cards are in a random order, right? And waiting around for them to jump up, okay, which they're not doing, right? And organize themselves back into the original beautiful deck of cards where you decided what order they would be in. You're going to say, okay, we're going to put all the aces first, followed by the kings, follow all the way down to the twos, and we're going to organize. First we'll put spades, then we'll put hearts, then we'll put clubs, and then we'll put the other guy that I can't remember. Okay, so we have hearts, spades, clubs, and diamonds, right? So we're going to put them in that order, right? A perfect order where every card we could predict exactly where it would be in the deck. That's not happening under any conditions. Why? Because it's uphill, and this guy over here, non-spontaneous at any temperature. Uphill and negative entropy, non-spontaneous at any temperature. So that's the one that we were doing. Sorry, these two come later. All right. So spontaneous at any temperature, downhill, more entropy, never spontaneous, non-spontaneous at all temperatures, uphill, and more organized, right? Go upstairs and clean your room. It's not happening, okay? Those things don't happen by themselves, right? Things automatically fall down and they go to more disorganization. All right, let's look at the math though. When I plug in, if this guy's if this guy's negative over here, a negative times a negative gives me a positive. And this guy we said was positive, so positive plus positive will always be positive. This one will always be positive, this one will always be negative. Okay, let's talk about the two counter situations where enthalpy is balanced by entropy. Okay, now look at the formula. Entropy is more important at high temperature because it's multiplied by temperature. So it's exaggerated or amplified. If you make the temperature 10 times higher, the entropy factor becomes 10 times more important. Okay, so let's look at this one here. I have an endothermic reaction. It doesn't want to happen at low temperatures under regular conditions. But if I heat the heck out of it, I can make it occur. Why? Because delta S is positive, right? So delta S is positive. If this guy is positive, this factor is going to be negative, and it's going to be more negative depending on what T is. So I may be able to get this negative term by having it multiplied by T to beat out this positive. So this negative is more than this positive, and then it'll be spontaneous. So it would be spontaneous at high temperatures when this side can overcome that guy. Remember, because we want delta G to be negative. So I can get this guy to be negative when this is bigger than this. Okay, so that would be uphill and more randomization. Okay, last case, exothermic, but going to more organization. I hate that. I hate organization. I like disorganization. Well, this guy's working with us, right? We love to go downhill. Downhill is natural. So that guy's good. So we want to minimize this term. We want to minimize the entropy. So if the entropy is negative because it's yucky and going toward more cleaning up your room, more organization, negative times T is still negative. This little thing will always be negative, right? Because T doesn't change it. But negative and a negative is a positive. So now I have two counter terms working against each other. Look up here. These guys were working together. Positive, positive, negative, negative. Okay? These guys are working against each other. So who's going to win? Well, if we want delta H to win, we want to do this at low temperature because this term over here, which is positive, is multiplied by T. So the lower the temperature, the more I minimize this part, this back part. And so at low temperature, I can get a chemical reaction to occur because H is with you and S is against you. So those are the four scenarios. Look for multiple choice questions where I ask you, under what conditions is a chemical reaction spontaneous? When delta H is negative and delta S is positive, there are four different cases. And here's the answers. Okay, so you got to memorize that. And again, you know all the temperatures in this whole chapter are always in Kelvin. Okay, that's 41 minutes for this video. That worked out great. I've got one more section. It'll be the fourth video for the thermodynamics chapter, chapter 19. Okay, bye everybody. Thanks again.